Welcome students in the session of semiconductor. Today we will start the introduction, a very important topic in the physics of the chapter semiconductor, which is important for the CBSE NEET as well as for the IIT JEE examination. So let's begin this beautiful topic with the first topic, energy band in the solid. So based on the Pauli exclusion principle, in an isolated atom, electron present in energy level, but in solid, atoms are not isolated. They are interaction among each other. This is due to the energy level splitted into the different energy level. Quantity of these different energy levels depends on the quantity of interacting the atom. Splitting of the sharp and closely compact energy level result into the energy band, and they are discrete in nature. Students, the mean of an isolated atom means those are not interacted with that anyone. Like if I'm just talking about you heard about the corona? Like last year in 2019, a strong virus is running in our society. So what people are doing? They are just doing isolate theirs itself. Means that pupils are isolated itself, because of that the other person not interact with them. So isolated means a particular particle, a particular thing which is not interacting any other one. So as we know about the solids, in a solid, atoms are not isolated, they are interacting with each other, as they have a different energy levels, so that if the electrons get gains the higher energy or gain the more energy, so it will be suddenly transmitted to the higher energy levels. So these are based on the energy levels. Because of that, there are splitting and sharp banders are allied. So order of energy levels in the band is 10 to the power 23, and their energy difference 10 to the power minus 23 electron volt. So the range of energy possessed by an electron in a solid is known as energy band. Now there will be a few types of a band, in which first we are considering valence band. Range of energies possessed by valence electron is known as valence band. They have bounded electrons, no flow of current due to such electrons, always fulfilled by the electrons. Next is a conduction band. So the range of energies possessed by the free electrons is known as conduction band. Means this is the actually criteria of electron which is responsible for current conduction. That's why we are saying as a conduction band which can possess the current. I hope you are understanding, students. Those are responsible to generate or to develop or to induce the current. So they are actually called as a, they are actually responsible for the conduction. So conduction band electrons are have electrons which are free. So as I told you, it has a conducting electron. Current can flow due to the such electrons. If conduction band is fully empty, then current conduction is not possible. See, if the band is successfully completely empty, so there is no free electrons. Simple. If there is no free electron, means no free electrons. So if there is no free electrons, so how the current can conduct? Because responsible person, responsible, yes, responsible person or a charges is only free electrons, which is not present over there. So that's why we are saying that conduction is not possible. So I hope this point is clear. Electrons may exist or not exist in it. Sorry. So electron may be or may not be consist that one. Means in the conduction band, it's not necessary that okay, electron must be there, free electrons must be exhibit. If there is a no free electrons, they can't exhibit the current. Like in the case of an inductor, same it will be happening because in the inductor, sorry, in the insulator, they don't have free electron. So if they don't have free electrons, so they can't exit, actually they can't conduct the current. That's why we are saying that in the case of an insulator, that in the conduction band there is no free electrons. Forbidden energy gaps. The energy gap between the conduction band and the valence band, where no free electrons can exist. See, there will be a levels of a part. As I told you, there was a level. So this is a, if I'm taking, this is a like conduction. This is a valence band. Okay, this is a conduction band. Okay, and if there is like if we give some energy to the valence band, an electron can drop out from the conduction band to valence band to conduction band. So it start to like conduct the current. In between there are energy gap. Okay, like in the insulator, this energy gap is really very high. Because of that, electron not transfer from valence band to conduction band. Okay, after giving the energy or but in the case of if I'm just taking the case of like conductor, that gap is very less. How much? Less than 3 electron volt. So in detail we will study these things, but now we are just taking the like small section of a part, that energy gap is the energy gap between the conduction band and valence band, where is a no free electron can exist there. So forbidden energy gap, which is represented by FEG, for example, like a conduction band is a minimum minus valence band is a maximum position, because if I'm just taking a width of a forbidden energy gap, it depends on the nature of the substance. See, like as I told you, like for the case of a conductor, the gap between the valence band and conduction band is very small in the nature. But similarly, if I'm just taking the another case, whereas if I'm just taking the another case, so in the case of insulator, that gap is very large in the amount. And the case of a superconductor, it's partially like superimposed. So it totally depends on that, like what kind of a material we are choosing. So different kind of a matter or substance behaving and responding the different kind of a like era. Next we are taking width is more, then valence electron are strongly attached with the nucleus. And width of the forbidden energy gap is represented in electron volt. As temperature increases, forbidden energy gap decreases very slightly. Classification of a solid, if I'm just taking like how we are just classified the solid. So on the basis of electrical conductivity, the solid are classified as, see student, as I just want to elaborate and explain you the things. Solid can be classified in the many forms, like electrical conductivity form. We can classify it by the nature, we can classify it by the materialistic nature, we can classify it by the behavior as well. They are responding with the temperature, different kind of a thing. So here what we are doing, on the basis of the electrical conductivity, we are what we are saying, the main thing which is here, which we are taking, that is the conductivity, like how solid conduct the charges. Okay, conduct the current, actually we are discussing about that scenarios. So the first conductors, semiconductors, third insulators. We did classification of a solid in three structures like conductor, semiconductor or insulator. Now, in the case of a metal, they possess very low resistivity or a high conductivity. The rho is in the order of 10 to the power minus 2 to 10 to the power minus 8 ohm meter. This is the actually resistivity. Because of that, as you can see the range 10 to the power minus 2 to 10 to the power minus 8, which is a very less in number. Insulator, they possessed very high resistivity, 10 to the power 8 ohm meter approximately. And the semiconductor, they are partially resistive. Okay, so they have a resistivity intermediate to the metal and insulator, that means 10 to the power 5 to 10 to the power 0 ohm meter. Elemental semiconductors, they say, if I'm just taking like a silicon and germanium, and a compound semiconductor like a Sirius and gallium arsenide, anthracene, polyline, etc. So, same, these are the substance which we are taking as a compound semiconductor. One by one, if I'm just taking like in a metallic conductor, like aluminium, copper, etc. The outer orbit electrons are shared by all the atoms, and the metallic crystal can be visualized as the positive inner cores embedded in a regular fashion in a sea of shared electrons. Such electrons are called free electrons. A small electric field causes the flow of these free electrons in the direction of a positive potential and current start flowing. For the case of insulator, the bounding situation is very much different. The outermost electrons remains bound to their present parent atom almost at all the temperature, and very high energies are required for these electrons to break away. Thus, the electron's conduction remains almost nil under moderate values of the electric field. So, in semiconductor, on the contrary, at moderate temperatures due to the thermal excitation, the bounded electron let themselves free and wander freely to give moderate value of a conductivity. See, but very low temperature near about the 0 Kelvin, the conductivity of the semiconductors is 0. Students, as you know that like if we are just contributing the temperature, if we are just giving the temperature very high temperature, so the molecules and the atoms is actually start to vibrate, and because of that vibration the bond must be break. Understood? So if we are just taking a normal temperature at a very low temperature, so semiconductor is a nothing. They behave like as an insulator. But as wherever we just raise the temperature, we just start to raise the temperature. Because of the raising temperature, the vibration occurs, and which is responsible for the bond breakage, and electron gets free for the conduction. I hope you understand, students. Energy band diagram. So this is a valence band, this is a conduction band. Valence band full with electrons, band gap where there will be there. Insulator, as you can see, there will be like a large band gap. In the semiconductor, very less an amount, and in the conductor they are overlapped, so that if valence electron get some energy, little bit kind of energy they can, they have it, so they just transfer, they just start to conduct the current. Understood? So as we can see in this comparison result, comparison between the conductor, semiconductor and insulator, temperature coefficient is a positive in nature. Current is due to the free electrons, which is a free energy gap is 0 electron volt, platinum, aluminum, copper, like Ag also. In the semiconductor, temperature coefficient is a negative. Current is due to the electrons and holes, and the forbidden energy gap is nearly 1 electron volt, which is a germanium, silicon, gallium arsenide. But in the case of insulator, temperature coefficient is a very slightly, that is a negative, no current. Forbidden energy gap is equals to that greater than 3 electron volt, which is a for plastic, wood, mica. So concept of a holes in semiconductor due to the external energy, temperature or radiation. When electrons goes from valence band to conduction band, there is some kind of a gap. There will be some kind of a vacancy are created. Okay, because the electrons are bounded from the free. So vacancy of the electron create in the valence band, which has the same charge as electron, but they are positive. See, simply if the electron if the electron is actually pressing there, okay, if we remove the electrons, so there will be a vacancy created, as we told, electron removed, so that places a positive. But if we just taking the charge of that, see, whole the system is a contemporary balanced. So if we just taking removing the electron, a self positive behaving like a electron are created, so that is a hole. This positively charged vacancy is termed as hole. So as we saw the earlier case, see here, these are the holes. As you can see, this electron, because of get higher temperature, thermal agitation, this electron becomes free to move. This is a free electrons. And because of this free electrons, a hole is created. So this is like their movement is actually virtually. The holes actually move, not actually move, they are virtually moves. But whose move actually? Electrons. Okay. The movement of electron is actually movement or original movement, but the movement of a holes is a virtual. So it is the deficiency of an electron in a valence band. It acts as a positive charge carrier. Its effective mass is more than that of electron. Its mobility is less than electron. Note that there is an important note: whole act as a virtual charge carriers. They are not, as I told you earlier, that they are not moving like real, but they are the movement of the electron. They are the movement of electron. Because of that, holes are moving. I hope you understand, students. So as you can see in this picture, effect of temperature in semiconductor. This is a silicon atom, okay, and we can take an as germanium, which they are bounded as a covalent bond, in which bounding we are like I'm just elaborating by this gaps, and there is atom of a silicon is placed over there. If we just give some kind of a thermal agitation or thermal energy, so the because of that vibration, electrons just start to move, and that electron is completely free for the conduction. There is slightly a hole is present over there, which is responsible for if this is a vacancy, so electron will be captured by this, and here the vacancy moves. If here will be the vacancy, electron will be jump like this, so here the vacancy is created. So right like that, hoses are not actually moving, but what moving? Yes, the electrons is a moving. Because of that movement of electron, we are saying that current is a conducted. Now, previous figure A shows that two-dimensional representation. Oh, oh, yes. So, like there will be some error will be happening. So, figure shows that two-dimensional representation for the silicon and germanium structure. It's an idealized picture, which is a no bonds are broken, such as the situation arises at the low temperature. But as the temperature increases, thermal energy available to the electrons helps to break away, becoming the free electrons, the conduction. So, And there will be some kind of a other method also which we can take, like a doping method we can take to desirable impurity. We can add the impurity so that conduction we can take place, or doping process like a exhibit of a like if we, there will be two methods simply. Let's try to understand. First, anyhow we can remove the some electrons, so because of the holes current will be start to conduct, and if we just add some more electrons, so they will be start to conduct current. What is a dopant? So added impurity in atom is called as a dopant. The impurity added may be 1 part of the million, like ppm. The dopant atom should take the position of a semiconductor atom in the lattice. The presence of the dopant atom should not distort the crystal lattice. The size of dopant atom should be almost the same as that of a crystal atom. And if I'm just talking about the concentration of a dopant atom, this should not be large, not more than 1% the crystal atom. There is an important note that it is to be noted that doping of a semiconductor increases its conductivity to great extent. Students, as I told you, I think you've heard about the cricket match also. Like during the cricket match, if the cricketer applying some drugs, means they are taking the some excess amount of energy to get his performance better. Okay, because if the that doping is actually for the drugs they are taking for like excess of energies, they get excess of energy for the better and great performance. Here similarly the things is happen. uh, what is happening, the RBC actually start to like the movement of a RBC is actually excited in that time of a cricketer body. So, but here is a what actually in a starting duration, there is a at the low temperature, if just taking the higher temperature, as we raise the temperature, the superconductor, the semiconductor actually start to convert it itself into the conductor. Understood. But what will be happen in the case of a low temperature? They behave as an insulator. But if we just doing the dopant here, like doping here, doping will be either two types, either like a trivalent or a pentavalent. Trivalent means there is a, we can say, deficiency of electron will be there, because of that force is created. And in the pentavalent, there will be excess of electron, which is responsible for the conduction. Understood? So there will be many types of things we can did. So classification of a superconductor is done by two way, like intrinsic or extrinsic. So the case of intrinsic, a semiconductor is pure in the form. Extrinsic, a semiconductor in which impurity is added, is called as extrinsic semiconductor. So one which we are taking like intrinsic semiconductor, in intrinsic semiconductor at 0 Kelvin, valence band is completely filled and conduction band is completely empty. So what happened? Intrinsic semiconductor is a pure insulator at 0 Kelvin. And at that temperature, above that 0 Kelvin, say room temperature, so valence band is a partially empty and conduction band is a partially filled. Therefore, it can conduct the current at room temperature. In this structure, as you can see, like conduction band, valence band is a completely filled, conduction band is completely empty, and energy gap is a less than 3 electron volt at a 0 uh, Kelvin temperature. But as you can see here, like valence band is a partially, conduction band is also filled. At the temperature is increases. So in the case of extrinsic semiconductor, a semiconductor in which impurity is added, and this is called as extrinsic semiconductor. Doping increases conductivity of the semiconductor. What is the mean of a doping, students? So as I told you earlier, if we just add the few impurities in that one semiconductor, in the given semiconductor sample, so that is called as doping. So it has a two type, P type semiconductor and N type semiconductor. This S means semi and C means conductor. So intrinsic semiconductor plus impurity is called as extrinsic semiconductor. N-type semiconductor, when a pure semiconductor silicon and germanium is doped by pentavalent impurity like a phosphorus, arsenic, bismuth. So these type of this type of things have four electrons in the outermost shell. But in this five electrons impurity, if we added, so one excess number of electrons will be there. These impurities atom which we donate free electrons to the conduction, that is, it is called as donor. Due to the donor impurity, free electrons increases very much. So it is called as an N-type semiconductor. By donating electron impurities, atom get positively charged. Hence, this is known as immobile donor positive ion. And in N-type semiconductor, free electrons are measured majority charge carriers are holes. So they are called as a minority charge carriers. So here just I want to explain you each and everything in a detailed version, students. Like as I told you, like N-type semiconductor, like intrinsic semiconductor are pure semiconductor. But if we add some impurities, so that converted into the impure, like impure semiconductor, which we are saying as a extrinsic semiconductor. So in extrinsic semiconductor, in N-type semiconductor, what we are taking, we are doing a pentavalent bond collaboration. Because of that, excess number of free electrons we just get it. And these free electrons, we can say donate. This impurity actually donate this free electron for the current conduction. So that's why we are saying as a donor impurity. Due to this donor impurities, free electron increases very much. So this is called as N-type semiconductor. By donating the electron impurities, like if the electron is actually donate itself for the current conduction, they get some positive charge which we are saying as an immobile donor positive ion. Clear? And because of that, N-type semiconductor free electrons are majorly. So holes are really in a very less in the case because excess number of free electrons will be present over there. So because of that, holes are as a minority. Hope you understand. In a p-type semiconductor, when a pure semiconductor is doped by trivalent impurity, bromine, aluminium, like andesite, gallium, so the outermost three electrons are balanced, okay, but one part is a vacant. That vacant part is act as in holes. So that holes actually the responsible member for the current conduction. Here, this impurity atom accepted the electrons because a vacancy is there. So, like nearby or neighbor electrons wants to fill that vacancy. So, because of that movement of electron occurs, that's why we are saying as this will be acceptor impurity because this is accept the electrons by neighbor. Here, holes is increases in very much amount. So, this is called as a p-type semiconductor, and impurity ions is known as immobile acceptor ions. So, when these impurity atoms accept that electrons, so that because of that, there will be some we can see are created, that is the number of holes increases because of that, so that it is called as a p-type semiconductor. And impurity ions known as immobile acceptor negative. Now moving ahead, in p-type semiconductor, free electrons are as a minority, but holes are majority charge carriers. Okay, this is an n-type, donor energy level. This is a acceptor high energy level. So as you can see, donor electron axis and acceptor holes axis. Electrically neutral, both are. Mass flow action in a semiconductor due to the thermal effect, generation of free electrons and holes takes place. Apart from this process of generation, recombination also occurs simultaneously, in which free electrons further recombine with holes. At equilibrium, rate of generation of a charge carries is equals to the rate of a recombination of a charge carriers. The recombinations occur due to the electron colliding with a whole larger value Ne or Nh. Higher is the probability of their recombination. So Ne into Nh is equals to Ni square. Electron hole combination. So it is necessarily to complete a bond. That electron is shared from the neighboring atom. And so that if I'm mistaking, the second case of electron recombines with the holes of a valence bond. So this process is known as electron hole recombination. And the breaking of the bonds of a generation of electron hole pair and completion of a bond due to the recombination is taking place continuously at equilibrium. The rate of generation becomes equal to the rate of a recombination, giving the fixed number of free electrons in the holes. So, in whole process, what we are actually learn, student, that how solids are behaving, different kind of a solids behaving in different scenarios. Some are behaving as an insulator, some are superconductors, some are semiconductor, and some are insulator as well. So in the case of like solid, because of the conduction, we can classify the solid into many forms, and these many forms have a different kind of a reasons also. Like some have high holes, some have a less holes, some have a high electron efficiency, some have very less electron efficiency. Accordingly, we categorize that one. We are just adding the impurities to the like we can conduct the current in any among of them. Yes, in some kind of solids we can't do the conduction process, but again it is the behavior of that particular metal sheet or the conductor or the solids. So this is all much about today's class. I hope you get the I hope you get the things in a very detailed version. If there will be any doubt, students, you can ask in the like comment section. Till there, thank you for watching this video.